Hello, everybody. Welcome to our final, last but not least, Robotics Pathways and Career Speaker Series. We're fortunate to have Dr. Zhen Zeng from JP Morgan Chase, one of our fabulous alums. Do you remember why we hold these seminars? Do you know what the number one question we get about our robotics undergraduate program? What's the question we're most asked? Yeah. What can I do with the robotics degree? Great answer, Isaac. That doesn't mean I'm going to give you extra credit, but yes, people always want to know. We've started this new fabulous undergraduate program in robotics. We have a new department. What can you do with a robotics degree? And while I have many great answers for that, about the salaries you can get, the amazing professional opportunities, the adventures you can have in robotics. Probably the best way for you to understand that is by seeing examples of fabulous people that have gone off to have amazing careers in robotics. And we're fortunate to have a number of great alumni who've been able to show what they can do. And Zhen is one of these people. I met Zhen for the first time in August 2015. That was when I used to be at Brown University. I came to Michigan because of the amazing things that were happening in robotics here. In fact, I came in the same year as Jim Harbaugh. By the way, did anybody see that game? So I got my postseason bling going on. This is my postseason chain, right? And so this is so hopefully we'll see good things on Saturday. And I think we got something for Georgia this year. I just want to say that, by the way. But Jen and I met in 2015, and we struck up a really great relationship. And eventually, Jen and I became collaborators, and I helped supervise her dissertation. And she's done many great things. Won Best Paper awards, has done great things, and then to publish her work and do amazing research. And then she decided she wants to be a financier, and went off to JP Morgan Chase. To do great things at the intersection of robotics and finance. And I'm really glad that she's here to tell her story and to provide some inspiration to all of you about what you could do as roboticists through our degree programs. And so with that, I'll give the floor over to Dr. Zhen Zeng.
Thank you, Chad. Just to make sure everyone can hear me all right? Awesome. So it's a great pleasure to be speaking here today. To be honest, the whole Robotics Institute didn't even exist before I started my PhD. So it's been a great, opportunity, I think, for all of you to be able to take courses and everything from a well-curated course list. But then as I graduate from University of Michigan, which isn't necessarily robotics degree, but I did do my PhD, like Chad mentioned, with him at Laboratory for Progress. And my focus was in robotics. Although Chad mentioned I went off to JP Morgan and then become a financier, but really at the bottom of my heart, I still identify myself as a roboticist. And to that, I believe we can do a lot of things that we can imagine, not just limited to all the topics that you're familiar with in robotics. So today, I'm going to talk about my journey from robotics to finance and how much fun I have having throughout the course. So right now, I'm a research scientist at JP Morgan. Previously, as I mentioned, I was doing my PhD with Professor Chad Jenkins. So just a quick, oh, there. All right, thank you.
All right.
Sorry about that. I guess we're all familiar with this scenario, right? Whenever you have robot demos, this happens. All right, so just really quick about me. So I did my undergrad at Shanghai Jiao Tong University, also with through a joint program in electrical engineering system. And I continued my PhD at University of Michigan, focused on robotics research. Mainly, my interest covers semantic robot programming, particularly robot perception for manipulation, as well as semantic mapping, 3D vision, and also active vision. Proudly, I have participated in top-tier conferences on robotics and also won several Best Paper awards. And now I'm in JP Morgan AI Research. I'm looking at how can I bring visual representations into the understanding of financial data and much more. So just as a quick visualization here at the bottom, This is my journey so far. I started off in computer vision, dealing with medical images, segmentation, and then I got interested into robotics because that's where the vision and action come into play together. And then, over the course, in the end, there are many unexpectations, right? Like, for example, in the end, I went to JP Morgan to become a research scientist in their AI research team. Before I dive into my journey, I'd like to quote Dr. Fauci, who definitely quoted another Irish poet as well, on expect the unexpected, and also stay heads up for an unanticipated opportunity should it present itself. All right, so just really quick about my initial exposures in terms of research, like computer vision. I was working with Professor Silvio Severis at his computer vision lab when he was back in University of Michigan. I focused on a couple of different topics like segmentation and 3D reconstruction from articulated motion, as well as hand tracking and real-time gesture recognition. But as I was working on those projects, oftentimes this question comes into my mind. I feel like something is missing, and I think it's interaction. So basically, whenever you deal with like object recognition or object detection, once you have that, what do you do after that? Like there is always this like, what do we do next? So in robot, I think I get the answer. So once you understand the environment, you can start to interact with them. Sorry. Sorry about that. Yeah, so that's why I joined separately, like chronologically, in Professor Benjamin Kuiper's lab in studying learning from demonstration on Baxter robot, and as well as later on joined Professor Chad Jenkins in his laboratory for progress on more onto robot perception for manipulation. So there is the very first unexpectation happened during my journey so far, which is, as you can see already, so I went to 2 different labs during my PhD. So for the very first half of my PhD, the unexpectation was that it took much longer time than I expected to figure out what I really want to do, to figure out what research topics I'm really interested in. But it was okay. So it took time, and thanks to the support of both Ben and Chad, I was able to transfer and also learn more, start to find my own voice in the field of robotics, and figuring out my real passion is on robot perception for manipulation, and finding out how can we use that to enable robots to be more assistive to humans in our daily lives. So just to give you a quick overview of the projects that I've involved in during my PhD, the overarching goal is semantic robot programming. And what do I mean by that? So you guys might be familiar with the term programming by demonstration or learning by imitation. Basically, with this, we're trying to enable a novice user, like non-robot experts, to go up to a robot and to easily express what is the goal of your task. And the robot should be able to comprehend that goal easily and go fulfill the task on its own without requesting help from the human. And here I'm just showing a bunch of popular videos that demonstrate motivating examples that assistive robots can help us with, right? For example, putting away objects, cleaning up mess, organizing tabletop, cleaning dishes, and even go ahead and then order and fetch food for people. And throughout my PhD, I aim to answer a couple of core questions. So the first is, how do we even describe the goal to the robot? How does a novice user, how can a novice user easily convey that goal to a robot? And the second is, once the robot understands the goal, how can the robot fulfill the task? And the third one is, how do we scale it up? Scale it up in the sense spatial-wise, right? So if you have a tabletop organizing task, how do we scale it up to a larger scale, like a room, for example? So to begin off with the first question, how to describe the goal to the robot. In the meantime, I'm going to answer the third question as well, how to fulfill the task. This is one of the works that we've done during my PhD with Jenkins. So our answer to that is, for user to convey a goal, the easiest way is to do it through a demonstration of a goal scene. Basically, what that means is that user can present an image of what is the desired final scene that you want the robot to achieve. And then the robot can use perception techniques to ground those into objects and into relations between those objects, and then represent that as a objective. And then through planning and execution, the robot can take whatever the current state of the world is, and then try to execute a sequence of actions to transit the state of the world from the current to the final goal state. And with that, I would like to use this video to explain to you how that's being done. So first of all, for example, a user can walk up to a robot, and this is a tray setting example. Bear with me because I'm not using really daily objects for tray setting example like breakfast, cereal, and so on. This is all the convenient objects that we can be using in the lab. But this is sufficient for the purpose of illustrating the capability of the robot. So basically, the robot is going to look at the goal scene and also the current scene and trying to parse them into what other objects are in the scene and what are the relations between the objects. And with this, the robot can use planning domain definition language. If you're familiar with, you can use strips planner, for example, to plan symbolic actions like pick and place actions to transit the world from left to right. And this is an example of the robot executing one of the tasks. So it's realizing what are the objects need to be put away and also what are the objects that need to be reorganized. And one of the key components here during planning is to figure out what are the preconditions between actions, what are the post-conditions between actions, so that you can make sure you clear out the top of an object before you stack another object onto it, for example. And this sequence of actions require very accurate localization or estimation of the object pose, as you can see, because if the estimation is off, then the robot won't be able to grasp them at the correct location, not to mention to place them at the proper pose. And this is a deep dive into how the overall mechanism we call digest that overall parses the scene into objects. Here I'm showing 4 different candidate hypotheses of what are the objects are in the scene. Why do we have candidates? Because we don't always have 100% accurate object detection. You could have object detections that give you erroneous class labels. So what we do is that we take the top, several confident detections, and then we compose different alternative hypotheses. And we assume that we have the 3D geometric model, like CAD model of the objects. And for each of those hypotheses, we try to render what is the actual depths of these objects, if these are the real objects in the scene, and then see how well they match the real world. And as you can see, after matching the rendered depth image and also the real observed depth image, we were able to finalize which hypothesis is the correct one. And this is just showing another example of that rendering happening and then showing this is matching the real observation. Again, representing them into axioms about objects and the relations, and then using planning domain definition language to express them, and then for the robot planning. So here the robot planning is all at the symbolic level. So we're not really doing any complex task and motion planning. A lot of that depends on the accuracy of the object pose estimation. So once you have the perception figured out, the robot is able to pick and place robustly with the objects. And you can see the remote controller there showing that we're not cheating. This is robot, operating on its own, not someone behind the scene. And here are just some more examples of setting up the tray. So each of these is an example of the starting scenario. And the top left corner is showing the ghosting that the user has demonstrated to the robot. And as the robot completes each task, it will be labeled red surrounding the box of the ghosting. I'm just gonna let it play till all the tasks is finished. All right. So with that, the robot can do all this tabletop perception, and also manipulating the objects to reorganizing the stacking relations and all the supporting relations between the objects. The next question is, how can we scale this up spatially from tabletop to larger rooms, for example? And if you're not familiar with this, I actually did experiments in the CSE student lounge where there's a little apartment kind of setup where you have sofa, you have different tables, you have shelves. It's a larger scale than a tabletop scenario. And here we're looking at a problem where if the robot is just driving across the environment, can we start to build up the map at scale with what we were doing already earlier, right, on estimating the objects, 3D poses, and also the relations, but also in the meantime becoming more robust. Why do I say that? Because the new challenges as we scale this up is that there can be a lot more occlusions between objects. There can be temporal consistencies that we need to consider between objects. So for example, let's say you visit this apartment-like place on day one and you come back, things might be replaced, right? The table might be moved to some other location slightly or completely different. And the object placements are gonna be different. And also the way you place objects are gonna be contextual dependent, right? Like depending on what section it is it the living room section, it is the kitchen room section, you would be expecting different kind of distributions of object classes to show up in there. So in that work, we proposed a work called CTMap, which stands for Contextual Temporal Mapping. And this is adding to the gap in the literature where usually when people look at 3D, 6D pose estimation of objects, they look at geometry of the objects, which is on the top left, which is basically, I'm gonna show in a second, but basically this is talking about the 3D geometry of objects and then fitting the known geometry to the observed geometry, right? But then they don't really consider the other three factors, or at least they don't unify all these factors together when estimating object poses, which is the temporal consistency. So for example, if the object is moved in local space, as well as contextual relations, like what kind of objects do you expect to co-occur more often? And that can help you correct like mistakes that object detection could be making. And I will give you specific examples for each. So let me click that. Right. So this is showing an example of the factor of geometry, correcting the errors of object detection. So on the left, we're showing the detection, which is erroneous. For example, this bowl is somehow misclassified into loofah, which has a completely different geometry. But now with that factor, we're able to correct that error based on the object geometry in the CTMap. And next, here we're showing that due to that table clause, right, you won't be able to detect a table at all. But because of temporal consistency, the robot has observed the table in that similar location before. And also there are objects somehow floating in the area. So with this, the robot is able to reason that there is a table and actually use the previous belief of where the table was to, again, resume the estimation of where the table could be now. So that results in that converged post-estimate of the table. And in this example, I'm showing for contextual relations. So this is a setup where it's more of a, like a bathroom setup, right? But you can see here, this shampoo is somehow misclassified into milk. I don't really blame the detector. I mean, it does look like a milk. But with the contextual relation, like what kind of objects co-occur usually with common sense knowledge, right? The robot is able to use that to correct that belief into it's an actual shampoo bottle instead of a milk bottle. So with this contextual temporal mapping, we're able to scale it up to a larger environment with more robust mapping and understanding of 60 pose of objects. Yeah, now the question is, now with all this, even if we scale it up, let's say we ask the robot to prepare cereal, like breakfast for us. And if there is no cereal box within the field of view, like even if the robot maps out the environment, it still doesn't see a cereal box in it. What can it do? So this requires the robot to have the ability to autonomously search for objects in an environment. And how can the robot do that? So like with a not so familiar environment, right? If the robot already knows like for example, your apartment where you place different objects, then it's a simply lookup table problem, right? But if the robot is not so familiar with your environment, the only thing it knows is like different categories of rooms. Like for example, this area is living room, that area is kitchen, that high level kind of understanding. How can the robot use that, exploit that kind of knowledge and effectively search for objects in the environment that are required for task completion? So this is one of the papers that we published at ICRA, and we won the Best Paper Award in both the Cognitive Robotics 2020 and also the Best Paper Award in High Accuracy Mobile Manipulation Workshop in 2019. The high-level idea here is that if the robot is looking for an object, for example, here showing on the left is looking for a coffee machine, the basic strategy for the robot to look for it is to reason about the co-occurrences between object and object, as well as object and places, right? So first of all, the robot can reason between the co-occurrences of coffee machine and also kitchen. So to quickly narrow down the search region, which is shown in step 2 here. So the robot moves from the living room to the kitchen to look for the coffee machine. But that's not narrowed down enough to pinpoint where the coffee machine could be, right? So what the robot can do further is that it looks around. Maybe a fridge is larger, it's easier to detect, right? But seeing a fridge is giving you a stronger signal of where the coffee machine could occur, like to the neighborhood of the fridge. And that could motivate the robot to navigate a bit closer to the fridge and then to look around and see if it finds the coffee machine. And of course, this is not an exhaustive search, routine where the robot basically looks for all the possible locations. We do have some trade-off strategy happening in the back end, which looks at the possibility, like how promising basically you're to find the object based on this common sense knowledge, but also what's the cost, navigation cost of the robot to go from wherever it is right now to the location it's going to search for the object. And I'm going to show you an example and explain in detail. Right. So here is an example of the robot looking for a cup. And again, this is at one of the student lounge, and it's quite cluttered with all kinds of objects, but it has a basic like apartment-like setup. So this is the kitchen area. The robot detects really quick, and it finds the sink area. and decides to look closer just to see if there's a cup in there. In this case, the robot was lucky because there was a cup right at the counter. Once it finds the cup, it can fetch it and return it to the user. And of course, we don't recommend that kind of move because if there's any liquid in that cup, it's going to spill it. We need more, right? We need better affordances understanding of objects. That was not within the scope of that project. So this is a quicker diving into what's happening behind the scene. So for the robot, it has a map of the environment and basic understanding of where the kitchen is, where the living room is, and all that. And here the robot is basically using particles as a way to represent the distribution of the belief of where objects could be. And it's simultaneously modeling where different objects could be, not just the cup, but also all the other objects that are relevant to cups. So in this case, the robot went to the sink, and as you saw earlier, it found the cup. And this is another example where it's not as lucky as this time. So first of all, again, it searches for cup, and again, every time I start this experiment, it's from scratch because it's not using any prior knowledge of the previous observational environment because we assume it's an unfamiliar environment. So next, the robot went up to the sink because probability-wise and also navigation cost-wise, that's the most optimal view post to go next. But this time, it didn't see a cup there at the sink area. So it comes back to the living room area. And then it finds a sofa and see how it's doing this like kind of secondary reasoning, not directly from sofa to cup, but actually sofa down to another object like table and then table and cup. And all this happens naturally by modeling all this co-occurrences, probabilities between objects, as well as trading off between like the promising or chances of finding an object, like how big the object is, for example, and also navigation cost.
Quick question for you. So that place that was in there.
Yeah.
What was that?
That was the student lounge at CSE building.
Oh, really? What was it called again?
Shea Betty? No.
Shea Betty. How was Shea Betty awesome?
Yes.
All right. How awesome was it?
It was great. I mean, it created a lot of like hard to navigate and then cluttered environment for us to test our robots on.
As well as candy and chips and Soylent, yes. Access to that 24/7, 365. So that was
do we still have that in robotics?
No comment. No comment.
I think one of the things that our lab mates, laboratory progress, talked about was in the new robotics building, it would be nice to have the robot to go up to that little self-checkout area and pick up food for you guys and then return it. So hopefully one day you'll see that happening. So let me move on to next. Right, so that was about where I ended my PhD, but thanks to Chad. So after my PhD, I still continued collaborating with a bunch of great collaborators from the lab, like Afonso, Xiaotong, Emily, and Xiao. And together we've done a lot of great works. For example, this one, we are looking at how can we relax the assumption of having a 3D CAD model of object. Like we cannot always assume the robot has the 3D geometry of an object, but we still want to manipulate and estimate the pose of these objects. So in this work, we looked at how can we learn a category level objects. Like no matter if it's a chair like this or different looking chair, can we have a canonical representation of the pose of the chair so that we know this is facing up, this is like the orientation. So the robot knows exactly how to manipulate them. And in here, I'm just showing a robot looking at all kinds of novel objects has never seen before. but being able to reason about what are the affordances that are observed in the cluttered environment, like container, right, like bowl and also spoon and also stir for the robot to complete some kitchen tasks, right, like pouring and stirring and all that. And on the right, I'm showing a work with Alphonsus as well on how can we enable the robot to pack objects in a very low cost way, without involving a bunch of like complex task and motion planning, which turns out to be very unnecessary and also reduces the success rate in our experiments. And just a quick mention of other works that we've been looking at. Can we enable robots to visually localize under object dynamics? So with all this visual navigation hype going on in computer vision, very little work talked about how could you enable such system to be robust to dynamics of objects and environment, and we focused on that. The other one is on how can we, the very last one but not the least, is with Emily on how can we enable robots to assembly objects with different kind of affordances, like rotating, screwing, and also like hammering. So this is what I've been doing after PhD. In the meantime, I have been starting my career at JP Morgan AI Research as a research scientist. This is just a quick overview of projects I'm involved in, but there's so many other things happening. But mainly, how does that connect to what I'm doing during my PhD? So for me, the main connection was that I focused on robot perception, and there's a lot of vision going on during my works. Here at AI Research at JP Morgan, I have been looking at how could we bring visual perspectives into finance, which is unique. Like no one has really thought about that before. I won't take the credit for that brilliant idea. I mean, Mawala is actually the one that thought about this, right? So basically, when they first started AI Research, they looked around the building and then they went to the trading floor. The very first thing they realized is people were having like so many screens on their desk, and they're looking at a lot of visualizations before they make decisions. And this is an instant strike like for them, and they were like, why don't we enable machines to do so? And that's naturally how computer vision can play a role here. So ever since I joined AI Research, I have been looking at different ways of understanding financial data. For example, financial time series, either univariate time series or multivariate time series. How could we use visual representations for those, and what kind of benefits we can get from those? So far, so far from the publications, if you're interested, you can go up online and search for it. We have discovered that using image representations, for example, of time series, we're able to forecast, the future stock price time series, for example, with much better performance using, if we're looking at the probabilistic forecasts. So which is something that, the numerical, if you just look at them as numbers, was not able to offer. And there are other lines of work which look at attention, right? Just looking at understanding how people, look at their screens, and for example, if they look at resumes, what are the important areas to look into? And these are really useful cues for people to develop autonomous agents to, do document summarization and narration, for example. And just more I want to mention is that ever since I joined AI Research, I have been finding more and more connections and overlaps between finance and robotics. So here are just some examples. For example, there are planning in finance, which winds all the way back to optimization and classic planning in AI. And of course, in robotics, we use that as well a lot. Also, so that's like used for example, in resource allocation, as you can imagine, and scheduling, right? Scheduling in terms of like tasks, right? How do you want to fulfill customers' requests over time? The other huge aspect in finance is market. How do you understand market? And in the end, market is composed by a lot of interacting agents. And these agents, each of them has their own policy that are evolving over time, right? So like this is all familiar terms if you guys are have done reinforcement learning in the past, for example, right? So how do you model markets such that you can replicate or almost mimic the evolution of the market with all these participating agents that you could have partial observability on or full observability depending on your assumptions. But once you have such model, it can be very useful for you to make predictions and also be robust to like unforeseeable changes in the markets. And the third one is reinforcement learning. So obviously, like in finance, there isn't much well-defined benchmarks, for example, or metrics of like they don't. In the end, they look at, I don't know, performance, profit, or something. So there isn't a well-defined way to guide your training, if there is any. So reinforcement learning is one way to get you there, right? So like without really understanding the step-by-step, like each stage's objective function, if you just have an end-to-end, the final reward function, you can still use reinforcement learning to see if you can learn a useful policy. And there is much more than that, but I'm only talking about works that we have been publishing so far. So here is a quick glance at the connection between robotics and finance. So with that, I would like to conclude my talk. As you can see, like throughout my journey, I have run into several different, unexpected changes, right? One is I changed my advisor during my PhD, and the very last one is I went from robotics to finance, which from the surface, you don't really see the connection at first. But I would like to quote Fauci again, but in the meantime, put my own interpretations there. So I think overall, robotics is a very multidisciplinary field. You are very easy to find connections between this and many other fields. And don't let expectations limit yourself. Yes. Thank you.
Dr. Zheng.